All right, so in this video here, we are going to be looking at simplifying basics for square roots. So we just have a quick little reminder that if ever you have a simple radical sign here and there's no index, then that by default means that it's a 2 in a square root, and also the square root of any number squared, and this is key for our simplifying, is in fact that number. And so it doesn't matter if you have a cube root and an x to the third, then it is x. And if you keep this in mind, this is going to be the foundation to simplifying square roots. So let's look at our initial fundamental. And so this definition is dealing directly with perfect squares. You won't always have perfect squares, but simplifying means to square root all of the perfect squares of a number. And we're going to talk more about that. And obviously, if this was a cube root, then we'd be looking for all the perfect cubes of a number, and etc., etc. So it's trying to find all of these situations. So instead of this complicated cube root of x to the cube, we can simplify it and just write x, or the square root of x squared. So every one of these groups that we can find, we're going to simplify them and just write x. And that's what we're going to be looking for. So part in order to be able to find that bit of information is the product rule for radicals. It says that if I have radical of a, radical of b being multiplied together, you can actually put them all under one enlarged radical. So an example would be if I had square root 2 times square root 3, then I can actually combine those by multiplication. That's what product means, is to multiply, and do 2 times 3, which is radical 6. And thus I have simplified this complicated expression down to just square root 6. Please feel free to pause the video at any time to copy down your information. Okay. So in addition, we have the factor rule, which is kind of the flip side. That's kind of the forward and backwards of math. That says if I am given a certain radical of a number, then I can actually break it down into its factors. And then from there, separate the factors and square root each one individually. So let's say I had, example would be square root 20. Well, 20 can be rewritten as the factors of 4 times 5, and then I can separate them into the square root of 4 and square root of 5. That can actually be simplified then down to 2 radical 5. And thus, this is the simplified version, because square root of 4 is 2, and well, we can't square root 5. And it's this simplified version of this, because we found that perfect square and square rooted it as our original definition talked about. So you can also see it possibly with variables. And again, we can separate them into 2 separate. We have the factors already, separate them into 2 different ones, and then take the square root of x squared, which is just x, and then radical y. And that is in fact the simplified version of this original expression. So our next bit of information is simplify until the radicand has no more factors that in this situation are perfect squares or perfect cubes or whatever you happen to have for your index. So if I have 32 x to the third, then I can factor my 32 as 16 times 2, again looking for that perfect square. And I can actually do the same thing with my variables, is I can rewrite it as its factors of x to the second and x to the 1. Notice I still have x to the third. And then from here, there's a couple different ways you can write it out to be able to get the same answer. I just went ahead and grouped my perfect squares together, so that way I could square root them and they would all come out. The square root of 16 is 4. The square root of x squared is x. And then I grouped my numbers that were left over that would not form a perfect square, like my 2 and my x1. And so then those are just residual and left over in my square root sign. So this is one way you can do it. If you notice, I underlined to group those together. Those are my perfect squares. Square root them and get my simplified answer. So the big thing is finding factors and breaking it down into factors that contain those perfect squares or perfect cubes, whatever you happen to be looking for. So here is an example. If you notice, I can break it into 3 groups of squares, and then my leftover and simplified. Again, feel free to pause the video whenever you need to be able to copy this information down. Radicands can be combined to create perfect squares that can then be simplified. So if this one, I could go from here using my product rule. I can multiply and combine within my radical and then either go straight to here to my answer, which is basically divided by 2, or can start simplifying it out. This is kind of a long way to do it, but I wanted to show you the steps. Okay. So 1 group, 2 group, 3 groups, 4 groups, so x to the 4th. And then last but not least is the quotient rule, which says, again, if I have one large radical containing the quotient, basically just means the answer to division, I can break it into 2 separate ones and square root each one individually. Or, since 3 is not a perfect square, sometimes you can actually divide first. 27 divided by 3, which is 9, and that is a perfect square, and divide. So if you can, divide ahead of time or take the square root ahead of time, and if not, then see if you can actually divide and see if that answer or its factors then have perfect square in them. All right, I hope these helped.